All right, now if we go to sodium chloride, let's go. What was ammonium? Ammonium nitrate. If we go to ammonium nitrate, what would we say? If I wanted one molecule of ammonium nitrate, how much does one molecule weigh? And what would you say? You'd say ammonium nitrate does not form molecules. So if I can't call it a molecule, then what should I call it? Yeah, formula unit. So how much does one formula unit of ammonium nitrate weigh? So we calculated this. This was what, 80.06 U per ammonium nitrate formula unit. You know, if you want to be more descriptive, and normally I try to be 80.06 U's worth of ammonium nitrate, NH4NO3, per 1 ammonium nitrate formula unit. And so here we would call this the formula mass. Formula mass. There'd be no molecular mass here because ammonium nitrate is an ionic compound. It doesn't form molecules. And then over here, the molar mass would be 80.06 grams per mole of formula units. I'll just call it. So this is a single formula unit, this is a mole of formula units. Or in other words, 80.06 grams of ammonium nitrate for every 1 mole of ammonium nitrate formula units. All right, so this one we would call the molar mass as well. And the formula mass can refer to two things. It can refer to U per unit, or it can refer to grams per mole of unit. So formula mass is a versatile term, but since its definition is not so strict, I mean, that is, since it's broadly defined, you don't know exactly what you're talking about. So we have other terms, which are more well defined. And so let's do another one, carbon 12. We know that there are 12 U in one carbon-12 atom. This is the definition of the U, but you know, this could also be called could this be called the molecular mass? No, because carbon-12 doesn't form molecules, unless it's a buckyball. Could this be called the formula mass? Yes, this could be called the formula mass, but the formula mass is, you know, the broad generic term. Maybe we could have a more specific term. But this is the formula mass, which is the same thing as the atomic mass in this case. Formula mass is equal to atomic mass, and that's okay for this. Now, that's to contrast, there's exactly 12 grams of carbon-12 and 1 mole of carbon-12 atoms. U carbon-12. And this one would be the molar mass here. Molar mass. The mass of a mole of units. And so this would not be the same as the atomic mass, but it would be the same as the formula mass. So those are some scenarios here. All right, calculate the amounts of calcium fluoride. Now they aren't talking about which mass. And so whatever mass we can calculate for calcium fluoride. So the first thing we need to know is what is its formula. The calcium is what charge? 2 plus. Fluoride is -1. So what ratio do we need these in? CaF2. Calcium fluoride. Now, because of the numbers are the same, but the units are different. You know, if you look at it, the numbers are the same, the units are different. Numbers are the same, units are different. Because of that, I'm not going to put in the units because we have a choice of units. We could either do U per unit or we could do grams per mole of units. And And so what we'll do is we'll just do the numbers. So let's take a look at calcium. If you take a look at calcium, its molar mass is to 2 decimal places what? 40.078, which we would round to. Yeah, and so we got 1 calcium at 40.08. And then we have 2 fluorines. Fluorine is 18.998, which we'd round to. Yeah, so we got 2 at 19.00. And so we got 40.08 plus 2 times 19 would be 38.00, which gives us 78.08. Yeah, 78.08. All right, this is for CaF2. And so there are two ways I could do this. 78.08 could mean this. 78.08 U per what? Okay, so I'm getting 78.08 U of calcium fluoride per molecule of calcium fluoride. Does calcium fluoride form molecules? No, it's a metal and non-metal. So it's going to form an ionic compound. And so what we'd say is if it doesn't form molecules, then we say it forms a formula unit. So per formula unit of calcium fluoride. And so 1 unit of calcium fluoride weighs 78.08 U. Alternatively, I can do this, we would call this what? We would call this a molecular mass? No, we can't use molecular mass because this doesn't form molecules. Instead, we have to use the fallback term, formula mass. All right, now if I had a mole of formula units, it would weigh 78.08 grams. So 78.08 grams of calcium fluoride in 1 mole of formula units, calcium fluoride, or 1 mole of calcium fluoride formula units. And so what should I call this mass? Well, this mass I can also call the formula mass. But again, it's a bit too vague, the term formula mass, because we use it for everything. Another word for this would be, or name for this would be, the molar mass, or molar mass. And so those are the masses for calcium fluoride. Let's see what they have in mind. They were going for the molar mass. So they had 1 calcium at 40.08, 2 fluorines at 19.00, and they get 78.08 grams per mole. And so this is the typical units of it. Molar masses are usually in grams per mole. Formula masses are, or molecular masses are usually U per molecule, U per unit. All right, the mole turns out to be a good size. You know, dozens way too small. We need something much bigger as far as counting units. And so this is 1 mole of iron. This is 1 mole of aluminum, 1 mole of nitrogen, 1 mole of mercury, 1 mole of sodium, 1 mole of copper. All of these have the same number of atoms or particles or molecules. This would be 6.022 times 10 to the 23rd iron atoms. Up here, this is different. This would be 6.022 times 10 to the 23rd nitrogen molecules, N2 molecules. Hydrates, I didn't talk much about hydrates in lecture, but I did talk about it on video part 2. Some crystals can accommodate water inside the lattice structure. And so this is copper. What's the charge on copper here? 2. Because sulfate is a 2-, so we know copper has to be 2. Copper, what are the typical charges? Is that 2,3, 1,2, or 2,4? 2,3, 1,2, or 2,4? It's a 1,2. Depending, you know, its positions in the 1,2. And so this would be cupric sulfate or copper 2 sulfate. Copper 2 sulfate. pentahydrate. Pentahydrate has 4 waters of hydration for every molecule or for every formula unit of copper 2 sulfate. There are 5 waters for every molecule of copper 2 sulfate or for every formula unit. What's the best answer? Does copper 2 sulfate form molecules or an ionic lattice? Ionic lattice. It consists of copper 2 ions, sulfate ions, and then waters get incorporated in there. It doesn't look wet because the water's actually, it's like a sponge, you know, a damp sponge. You know? A damp sponge in the sense that, you know, it's not wet. Well, these aren't wet, there's no water there, but these are, I guess, damp crystals maybe. Versus anhydrous. We have hydrated and anhydrous. Anhydrous just means dehydrated, basically. Okay, here's a mole of mercury 2 oxide, HGO. Here's a mole of water. A mole of water is 18 milliliters. That mole of water contains an Avogadro's number's worth of water molecules. So that would be 6.022 times 10 to the 23rd water molecules in there. Here's a mole of oxalic acid. This is the dehydrated or anhydrous form. This is the hydrate. This is called oxalic acid dihydrate. It turns out you can't fit as many waters in the crystal lattice here. You can only fit 2 waters in the crystal lattice. Over here we could fit up to 5 waters. And so what would we say? Would we say, what would the best answer here be? 2 water molecules for every formula unit of oxalic acid, or 2 water molecules for every molecule of oxalic acid? What would be better? 2 water molecules per formula unit or 2 water molecules per molecule? Formula unit is correct, it's not wrong, but it's not the best answer. The best answer would be 2 water molecules per molecule of oxalic acid, because oxalic acid forms molecules, whereas copper 2 sulfate forms a lattice type structure. All right, so very common conversion, which I showed earlier, is the number of units to moles and moles to number of units. But this one's even more common. We have gram to mole conversion or mole to gram conversion. Very common. For gram to mole conversion, we'll have the molar mass. That is, for example, 12.01 grams of carbon atoms per mole of carbon atoms. So we use that for this one here. And this one, we flip it upside down. 1 mole of carbon atoms weighs 12.01 grams. Okay, so gram to mole, mole to gram conversion. So how many grams of compound do you measure out? Laboratory reaction requires 0.0360 moles of barium chloride. So we have 0.0360. What's the formula for barium chloride? What is barium? Ba charge? Well, if you have the periodic table, then you can see it. Ba is here, so what's the charge on Ba? Yeah. 2 plus. Ba 2 plus. Chloride? Minus. So formula? 1 Ba and how many chloride? BaCl2. So I have 0.0360 moles of BaCl2. Should I say I have 0.0360 moles of BaCl2 molecules? Or should I say I have 0.0360 moles of BaCl2 formula units? Which is the better answer? formula units. It doesn't form molecules. This formula units is the only choice we have. So 0.0360 moles of barium chloride formula units. A certain number. You know, it's like a half dozen. I have a half dozen units. BaCl2 units. I have 6 BaCl2 units. 0.0360. I'm going to have a certain number of those. In this case, we don't want to go to number of units. We want to go to grams. And so mole to gram conversion is very common. In order to do a mole to gram conversion, we need the molar mass. So let's get the molar mass of BaCl2. Actually, let's just do it ourselves for practice. All right, I'd like to go 2 decimal places for compounds. So barium is 137.328. And so I'll call barium 137 point what? 33. Okay, chlorine. I have 2 of those. Chlorine's common, I know it already. 35.45. This is going to give me 70.90. So let's add these 2 up. That's 3, 12, 8. Wait, yeah, 8. 208.23. 208.23. That's for BaCl2. And so I'd read this as 208.23 for BaCl2 formula unit, or 208.23 grams per mole of BaCl2 formula unit. And so I'm going to write this over here, 208.23 grams of BaCl2 for every 1 mole of BaCl2 formula units. So this should give me the number of grams. Let's take a look here. Again, you can see how the book does it. The book likes to keep the sig figs consistent throughout. So they're using 4 sig figs for barium, 4 sig figs for each chlorine. Now the problem is that, you know, when we're doing the addition, it's the decimal places, so this is going to bring the decimal place up 1. So I just keep it to 2 decimal places. I get 208.23, so my number is a little bit different, so I'm going to do the calculation. 0.036 times 208.23 gives me 7.49. 7.49, how many sig figs am I allowed? Looks like 3 sig figs. And so I get the same answer as them. 7.50 after rounding grams of barium chloride. And so a quarter mole of barium chloride weighs about 7.5 grams. Half a mole would weigh about 15 grams. And a full mole should weigh about 30 grams. That's right. Maybe my calculation's wrong. So these are some of the conversions here. We did units to moles using Avogadro's number, 6.022 times 10 to the 23rd units per mole. And the moles to grams using the molar mass. You know, moles converted to grams. We can also go grams to moles by inverting the molar mass here. Molar mass is mm. And then we can go moles to units using Avogadro's number, 6.022 times 10 to the 23rd. So these are common conversions here. These are shown back to back, but we don't have to do these back to back. We can go in any direction we want. In fact, when we go any direction we want, we usually generate a map like this showing us, you know, all the possible directions. So far, this is our map here. It's not much there, but here we can go from grams to moles, moles to number. Or we can go from number of particles to moles, number of moles to grams. Or we could just go halfway in this manner. It's just showing us all the options there. To determine the mass in grams of 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. All right, so the first thing is, what's the formula for sulfur tetrafluoride? Sulfur tetrafluoride. Well, one thing is, it's not an ionic compound. How do I know? Because we're using tetra. You know, tetra, di, tri, all those things are not for ionic compound, they're for molecular compound. And so how many sulfurs do we have? Actually one, otherwise they'd have to call it disulfur. Like, but since they're just calling it sulfur, it's just gonna be one. How many fluorines? 4. So this would be sulfur tetrafluoride. Now sulfur tetrafluoride, is that molecular or is that ionic? It's molecular. You know, this is binary molecular compound. It's not ionic. You know, although fluoride's ionic, but sulfur, you know, normally we don't think of it. So it's a little bit tricky. This is molecular because it's made up of nonmetals, and those nonmetals don't form common ions that we've seen, like for sulfur, common cations. All right, so what we have is 3.2 times 10 to the 24 molecules. So 3.2 times 10 to the 24 SF4 molecules is a lot. And then we want to get to grams. So we need something that gets rid of molecules. One thing that gets rid of molecules is Avogadro's number, 6.022 times 10 to the 23rd molecules per mole of molecules. I have a mole of molecules, and I got that many. And so the molecules cancel out. Leaves me with moles of molecules, or just moles. And then I need to get rid of moles, or moles of SF4. Let's get rid of moles of SF4 molecules. And I can do that using the molar mass. I know how much moles of different things weigh. And so sulfur is a 3207, and then we have 4 fluorines. Each fluorine is 19, so 2 of them was 38. 4 of them will be 76. It's going to be 76 total U. And so this is 98.07.
308.
I'm seeing 108. All right, 108. You're right. 108.07. Now we have different units we could use, but we're doing it per mole, so it's 108.07 grams of SF4 molecules per 1 mole of SF4 molecules. So the moles of molecules cancel, and that leaves us with grams. Let's figure out how many grams we got here. Well, let's see their numbers here. The difference is they're using 3206 for sulfur. We use 3207 for sulfur. And so their number is slightly off from ours. So I'm going to go ahead and calculate it then. All right. 3.2 times 10 to the 24 divided by 6.02 times 10 to the 23rd times 108.07. 574. 574.4 grams, which rounds to 5.7 times 10 to the 4, 10, not 10 to the 4, 10 squared grams. 500 or 570 grams. This is a lot of molecules, so it's going to weigh something significant. Okay, we'll stop here.